To my presentation. The topic of my paper is conditional execution of transpiler process based on per script feature detection. And in this paper, I present a architectural change to the Google Closure compiler, which is used to build nearly all of the production web applications at Google. It is an open source compiler, and so it is also used externally by several other companies to build their production web applications. Because it's a compiler for the web, it essentially compiles JavaScript. It accepts JavaScript as the source code for the input. So even if the web applications are written in other languages like TypeScript or any other languages, they are translated first into JavaScript and then fed into the Google Closure compiler. And so we'll see what changes we made to the compiler in terms of the compiler architecture and what impact it had. Speaking of the input sources to the compiler, right? JavaScript is a very rapidly evolving language right now. So in order to understand the changes we made, let's take a quick look at the evolution of the language itself. The formal language specification of JavaScript is called ECMAScript. And it is standardized by an international committee, Technical Committee 39, TC39 for short, under the ECMA International Standardization Body. And for the first decade or so, the language moved at a very glacial pace, very slow pace, until 2009, where ES5 as a standard was finalized for the language as a spec. And it is universally the lowest level that is considered for JavaScript, even though there is an ES3, just slightly lower than that. And until 2015, there weren't any major changes made to the language. But in 2015, TC39 finalized the ES6 spec, which was a drastic paradigm shift in the language because it introduced a lot of modern language features such as classes, arrow functions, and let and const keywords to have narrowly scoped variables. And since then, the language has new features every year, ES 2016 all the way until ES 2024, 2025. So you may wonder, other languages evolve too. So why does this matter so much for JavaScript and for the purpose of our presentation? This matters because compiling and distributing JavaScript applications, large-scale JavaScript applications, is fundamentally different from compiling and distributing traditional systems languages like C++ or Java or Rust for that matter, mainly because the runtime is very predictable. So when you build a C++ binary, you use a compiler of your preference, GCC or Clang, and you build it for a target hardware architecture which has a fixed ISA. The web development world is quite different from that, where you don't really ship final executable binaries, but you ship raw, minified, and optimized plain text JavaScript over the internet to the end users. And in the end users, the devices that the users may be having, they could have a variety of browsers running there. So you could have someone using the same web application on an iPhone with the latest Safari browser, and someone else using a legacy Internet Explorer on a Windows workstation. So the runtimes are very unpredictable, and this can be a problem because not all runtimes will understand all the language versions that the developers write their code in. And for that reason, developers typically force the web compilers to output a very lower level that is either ES5 or ES6. And yes, this is ES5 from the 2009 finalized spec. And they do this to ensure runtime compatibility so that even though they write their code using modern language constructs and modern syntax, it should work across all runtimes that the end users may have. And we call this transpilation. Transpilation is a popular term, started getting popular in 2013 onwards, mostly, and has many definitions if you look up online. But for the purpose of our work, we mostly define it as converting the source code that's written in one high-level language into an older, different version of the same language. And with that definition, Google Closure compiler has transpilation as one of the key main steps in its compilation pipeline. We run several compiler passes that are very narrow and atomic in nature. They transform a feature from a language level L into a previous equivalent AST using features only from a language level L-1, so lower language level than the syntax, than the language level that defines that syntax. And we do this by running these transpiler passes on a AST representation of the input source code. So for historical reasons, the compiler operates directly on the AST itself. So all the analysis passes are done through traversals on the syntax tree, and the mutations are also done on the AST directly. And this is one example of a transpilation that we do in the Closure compiler. This is a ECMAScript 2020 syntax called optional chaining, which they had added to improve developer productivity and efficiency, and it makes writing code much easier. But we have to translate that down to the final ECMAScript 5 level using a slightly more verbose syntax. And this is also a rough representation of that syntax because in reality there are a few more null and undefined checks in there that we have to take care of. But this is one example of transpilation that we perform. So let's zoom in on a transpiler pass really and understand why it is quite expensive. For any large-scale web applications, the abstract syntax tree representation may have thousands or tens of thousands of scripts, individual JavaScripts, and each script can easily have millions or tens of millions of nodes sometimes in the representation. And each transpiler pass must traverse across all the AST nodes of the script and find the specific syntaxes or features that it's trying to lower, and then perform those replacements in the AST. Along with that, it also performs some cleanups and updates the compiler states as it goes across all the scripts one by one. And as you can imagine, doing that for thousands of scripts with millions of nodes in each script can be very computationally very expensive. And now imagine that that was just one pass, but we have a series of atomic transpiler passes that run one after another in the compiler. So the time complexity really explodes. Computational cost really explodes in the pipeline. So let's say a developer sets input level as 2020, so they can use modern language features up to ES 2020, and they want to output ES5 to ensure runtime compatibility. That would mean that the compiler would queue up all the passes from ECMAScript 2020 all the way down to ECMAScript 5, and each of those passes would run on all the scripts in order to find those specific features and lower those features in the scripts. And the time complexity, as you can see, would be something along the lines of number of scripts multiplied by the number of nodes in a script multiplied by the number of passes, or the number of features if we assume that each pass is very targeted and removes one feature, which is mostly the case in the Google Closure compiler. So we know that transpiling is very expensive in this legacy flow. So what can we do to improve the computational cost and efficiency? There are a few key insights when we thought about this problem. And the first is that each pass is very narrow and targeted in terms of the feature that it removes. So we can very cleanly define what specific feature it's going to target. The second insight is it may be feasible for us to actually track what are the live features that exist in a script at any given point during the transpilation. And the third is we can also prohibit, because we organize our passes such that the modern passes run first and the older syntax gets removed later, and that is intentional by design, we can enforce downward monotonicity that prohibits subsequent passes from bringing back any features that a previous pass has removed. So that's what we did. Essentially, we satisfied all of these three conditions, and that allowed us to selectively execute or skip our transpiler passes on the basis of certain condition. So really what we do is we know what features exist in a given script, and we know what feature a pass targets, So on the basis of that, we skip a pass P on a script S if that script S does not contain any features that are removed by P. So that is the core idea behind the improvement that we made. And a few key implementation aspects of this were we leveraged as much as possible the existing architecture and the downward monotonicity of the phase optimizer that exists in the Google Closure compiler already. So the parser essentially records all the features that it sees on a script as a bit mask on the script nodes in the AST itself. So this is very minimal memory overhead. And then we added a predicate where every transpiler pass queries the script feature set to decide whether it wants to run on the script or skip the script. And this is basically checking whether the feature that's lowered by the pass exists on that script or not. And if it does not, then it just skips traversing the entire subtree of that script. And the third thing that was important for us to do was we wanted to have accuracy in the feature set at every point in the transpiler. So every transpiler pass has a responsibility of updating the script's feature set after it's done executing on the script. So essentially what this means is I have traversed this script fully, I have rewritten this particular feature from this script, so that's removed from the script feature set. But in doing so, I may have added a new synthetic feature from a lower language level, and so I'm going to add that to the feature set again, so that any subsequent passes that are going to run will recognize that there's this new synthetic feature that this pass had added, and I'm going to have to remove that. So dynamic feature set tracking was very critical for this to work, and we implemented that. To give a comparison of a very high-level comparison of the flow before and after we made this change. As you can see in the legacy flow, when a transpiler pass begins, it basically executes unconditionally one script at a time, does the traversal and does all the rewritings on the AST directly until it finds the last script. And once it does, then we move on to the next transpiler pass, which will be targeting another feature and trying to lower it to a lower language level. But the optimized flow, we added, like I mentioned, we added a predicate first. So as a transpiler pass is executing on scripts, it first checks whether the script contains my feature or not. And if yes, then it executes the pass on that particular script, which means does the traversal and rewritings. And it updates the script's feature set and updates the compiler state that it has removed this feature from the script. And if the predicate fails, it basically has to do nothing, and it just skips the script because there's no relevant features for this pass in that script, and it moves on to the next script. So this was the optimized flow of the algorithm after we made the improvement. So now we recognize that because we are dynamically skipping passes, there is a risk of feature leakage. Basically, we don't want to skip running a pass on a script accidentally and miss lowering certain features, because the way these kinds of errors manifest is at runtime, the end user devices, the JavaScript engine in the browser in Chrome or SpiderMonkey or JavaScript core, depending on the device, it would fail to even recognize the modern syntax and just crash. And that's a very ugly crash. So we want to have some architectural safeguards to prevent this feature leakage. And for that, we have a few things. We assert statically the pass order in the compiler itself, and it is very trivial to do. At the end of execution of every pass, the compiler validates that the compiler state exactly matches what the transpiler pass is updating after having run on all the scripts. We also have an AST validator, which is a development mode only because it's expensive to run. But this validator runs after every pass in the dev mode, and it cross-references the actual AST. It scans the actual AST, extracts all the features that it saw in every script, and matches, cross-checks that with the compiler's internal state and data structures, and reports an error if any pass is reintroducing a feature that the compiler thinks was already lowered. So that's one more check. And then we have a final post-transpile pass that is a very lightweight pass, which basically compares the compiler's data structures and compares them with the output level that the user has set, and makes sure that there are no features that exist in the compiler state that are unsupported by the output level. And besides these, we also have all the entire suite of testing that we did internally. So evaluation of this on Google workloads showed that most importantly, almost like 30 to 40% of the traversals that we were doing in the transpiler on select large-scale Google applications, and these include applications which are very diverse, including Gmail, Maps, Photos, Drive, every major large-scale application you can think of. We were doing significant number of redundant traversals over scripts, and across the fleet, we got 50% faster in our total transpilation time. And the paper also had some artifacts that I provided, which had contrived JavaScript sources over which you can run the solution. And that also showed great performance in the total compile time of those JavaScript source files. And this solution is also checked into the open source, so you can also take a look if you're curious. The final thoughts or takeaways is this easy to generalize to non-transpiler passes? No, it's not very easy because transpiler passes are very narrow and focused, and they know exactly what features they're going to lower. But if you think of very broad general optimizations like dead code elimination, where you're removing like entire functions or basic blocks, you may actually remove a whole bunch of features at the same time, and it's very hard to track what got removed. And we also have some things like cross-module code motion, where we move code blocks across scripts, and it will be incredibly hard to track what features got moved to which scripts, and then selectively skip passes on those scripts. But it is theoretically possible, and it's an area of which should be researched a bit more. But this is very easy to do for transpiler passes, and similarly for certain category of checks passes, where we're looking for very specific things in the source code. The key takeaways are: don't pay the cost for what you don't use. So if your application is very scarcely using select features, let's say out of 1,000 scripts, only 100 scripts are using this very niche feature, then you don't need to run the expensive transpiler process on all the 1,000 scripts. You only need to run it on the scripts that are actually using the novel feature. And with this work, we also showed that by doing lightweight analysis, we can get significant performance improvement and not compromise on correctness because of the architectural safeguards that I shared earlier. So yeah, I think it's a great blueprint for modern compilers that wish to incorporate something like this for their compile time or reducing their computational cost. That's all I had.
Any questions? No questions. So I got a couple of questions. So first, did you do any ablation study to break down the savings? Is it, for example, is it just a couple of transpilation passes that dominate the savings, or is it relatively evenly distributed?
Yes, we did some level of studies where we have something called as a tracer mode within the Google Closure compiler, which allows you to look at the individual times of every pass. And using that, we looked at how much time we were spending in like different transpiler passes as they were going through the pipeline. Typically, there was a pattern we noticed was that because the language evolves so rapidly, the modern features or the newest features are very scarce in the entire application sources. So let's say Gmail or some other large-scale web application has tens of thousands of scripts in it. Only like a few hundred would have the latest feature that was released like this year or last year and added to the spec. And in those cases, we saw the largest savings because we were running a lot of redundant traversals over those remaining scripts which did not have the features. So optional chaining was one of the examples that I showed, which initially had a lot of redundant traversals because it was not a popular feature back in 2022, 2021, but now it's very prevalent across the code base. So yes, we did do that.
Okay, great. Let's have a speaker again.
Thank
and
you.
I guess we can go to lunch, which gives us a little